Uh, Irodov problem once again. This is 3.149 from current electricity section, and this problem is about the resistivity of a resistor and how it varies with temperature. So we know that if it's a conductor, its resistance increases with temperature, given by the relation R is equal to R naught 1 plus alpha T. And in this problem, we are given two resistors. The resistor conductor 2 is neta times that of conductor I. So let's say one resistor is R and the other one is going to be neta times of R. And what they are saying is their temperature coefficients are alpha 2 and this one is alpha 1. And find the temperature coefficient of the resistance of a circuit segment consisting of these two resistors when they are connected in series. When we connected them in the series, their equivalent resistance R, let's call it R series, is equal to neta times of R plus R, or we can write it as neta times of 1 times of R. And now this equivalent resistance will have some equivalent thermal coefficient. So let's write the resistors in terms of their temperature coefficient. So we have RT2 is equal to neta times of R multiplied by 1 plus alpha 2 times of T. This is for this neta resistor. Its resistance at temperature T, resistance of the second resistance at temperature T is given by neta R 1 plus alpha 2 times T. And the same thing for resistance R. I will call it RT1 is equal to R1 plus alpha 1 times of T. And their equivalent resistance RT1 plus RT2. We can also say RS is equal to RT2 plus RT1, and from here we can find out neta R1 plus alpha 2T plus R1 plus alpha 1 T. And we are trying to express RT in terms of something like this equation, and then we can find out this coefficient from here. This will be equal to neta R plus R plus neta alpha 2 plus alpha 1 times of R into T, capital R into T. We can write it as R into neta plus 1 plus neta alpha 2 plus alpha 1 times of RT. So this is the series, the resistance at temperature T of this series combination, and this is the temperature, the resistance of this resistor, series combination of the resistor at temperature 0 degree centigrade. So what I am trying to do is express this series combination resistance at temperature T in terms of its resistance at 0 degree centigrade. We will take R neta plus 1 terms common. It will become R neta plus 1. This becomes 1 plus, and then this neta plus 1 gets divided by 1. Neta alpha 2 plus alpha 1 divided by neta plus 1 into T. And if this R series resistor at temperature T is this much, what it means is that if we compare this term, then this is the temperature coefficient, its temperature coefficient. So we can write temperature coefficient at T will be equal to this whole term, neta alpha 2 plus alpha 1 divided by neta plus 1. So that is for the series part. And in the next part B, we are required to do the same thing for the parallel resistor. So for the parallel resistance, the individual resistors have this temperature coefficients varying like this, and for the parallel combination the equivalent resistance R equivalent, if we can write R equivalent, R parallel, let's say R parallel at 0 degree centigrade, this will be neta R into R divided by neta R plus R, which will be equal to neta divided by neta plus 1 times of R. And then at temperature T, they have this resistance. If we try to find out their equivalent resistance at temperature T, then this will be something like R parallel at temperature T will be equal to RT2 into RT1 divided by RT1 plus RT2. And if you try to do these things, and this becomes R neta R1 plus alpha 2T into R into 1 plus alpha 1T divided by neta R 1 plus alpha 2T into R 1 plus alpha 1T. Now, if we try to simplify this thing, trying to bring this whole equation in terms of something like this term, and if we could take neta divided by neta 1 plus R, we would find the solution. The problem with this approach is we have a T square term in the above as well as in the below here. Oh, this is plus. So this is the square term here and this is the T terms here. The things don't get simplified. That means if we proceed in this method, it's very hard to solve the problem. So what we do is we try to do some tricks here, and instead of writing the equivalent resistor here, let's try this way. Let's try 1 upon R parallel at temperature T is equal to 1 upon RT1 plus 1 upon RT2. 1 upon RT1 is 1 upon R 1 plus alpha 1 into T plus 1 upon neta R 1 plus alpha 2T. Now we use the fact that alpha is a very small quantity. Alpha is something like 0.0000 many zeros and then 1 degree centigrade per degree rise in temperature. This temperature T is usually not that big. What it means that this bracket should be here. So if this alpha is a very small quantity, we can write 1 plus alpha 1T to the power of minus 1 as 1 minus alpha 1T. And the same thing for alpha 2. If alpha 1 and alpha were not a very small quantity, we would not have writing. So we write it approximately, this thing is approximately equal to 1 upon R multiplied by 1 plus alpha 1T, 1 minus alpha 1T, plus 1 upon neta R multiplied by 1 minus alpha 2T. And from here I take 1 upon R common. In fact, neta R both common. 1 upon neta R common. And this, I introduce the term neta here. Neta times of 1 minus alpha 1T plus 1 minus alpha 2T. This is 1 upon R in parallel. And I can recombine these terms, write as 1 upon neta R, neta plus 1 minus, this thing becomes neta alpha 1 plus alpha 2 times of T. So with this, I can write RPT is equal to inverse of this neta R 1 upon neta plus 1 minus neta alpha 1 plus alpha 2 times of T. What I do is I take out the neta 1 plus 1, neta plus 1 term outside. I get neta R divided by neta plus 1, and this thing becomes 1 1 minus neta alpha 1 plus alpha 2 into t divided by neta plus 1. And once again, the term alpha 2, alpha 1 and alpha 2, they are very small. And therefore, we can write 1 upon 1 minus alpha t, whatever this terms t, as equal to, apply the same formula here, we get this is equal to neta r divided by neta plus r 1 plus neta alpha 1 plus alpha 2 divided by neta plus 1 into t. And now this whole thing is its resistance of these two parallel resistors at temperature T is equal to 0. So this is the temperature at T equal to 0, and this is the parallel resistance at temperature T, and 1 plus this whole thing multiplied by times T. That means this whole thing is the temperature coefficient at temperature T, which is given by, if I call it, let's say, alpha T of parallel is equal to neta alpha 1 plus alpha 2 whole thing divided by neta plus 1. So for the temperature coefficients, things like that, the only thing you need to keep in mind to solve these problems in real world as well is that alpha is a very small quantity, and you apply the things, this formula, wherever it's required.